let's go into a little bit of we saw that the biology seems to interact with all this information, and it seems to confirm a lot of the information. So we can come at it from different perspectives. And one of the perspectives I was coming at it from is the geometric perspective, obviously. And I was playing with the interaction of the spheres interacting. If you put a sphere around each tetrahedron of vector equilibrium, they will intersect. Or if you put a sphere around each tetrahedron of a star tetrahedron, they will intersect. The intersection pattern looks like this. It looks like petals or lobes. Interestingly, the lobes, vertices, match the vertices of the octahedron cavity inside the metric. That is, they don't fall at weird angles or anything. They just fall directly at the vertices of the geometry. So now you have curved space interacting with linear geometric space. And I start to ask myself these questions, like, what are these lobe-type structures? Now, let's go back in time. I was still in my van. This was like 4 years later, right? And still studying, and I was reading a lot of physics about waveforms and so on. And it was really intriguing, but it was giving me a lot of headaches. And I was getting headaches because when you look at those things, waves, they typically are represented as a sine wave, right? Something in this fashion. And we are given in general that this is the wave frequency, the wave amplitude, and the wavelength. And that's basically the parameters we describe in wave dynamics. And I was getting a headache, and I couldn't figure it out. I was like not able to visualize these waves. I was trying to visualize my view of the universe, and to like see how the wave dynamics kind of fall into it. How does that all interact, and where it all fits in? And I didn't quite understand what a wave was, and so I was trying to read up on it, and I was getting more and more confused. And eventually I just said, okay, I got to kind of go back to the basics. And so I drove my van up to Alpine Lake in Canada, where, you have those turquoise Alpine Lake inside inside a mountains range, so it's very calm. And I grabbed a bunch of pebbles, and I was sitting on a branch on the side of the lake, throwing pebbles in the lake, going, okay, how are these waves working, And I'm looking at these rings coming off the surface and all this. And, it's kind of a simple approach, but I was kind of visualizing it. And I could see that if I took the waveform on the surface of the water and I sheared them, or if I divided them, I could see that it would generate this pattern, this waveform. But I thought, well, this is kind of an artificial way of looking at it, because, well, the rock is sinking. It hits the surface tension of the water, and then it pushes the molecules out, and then this wave comes out. And I thought, well, you have to account that the rock has to sink in order for the wave to happen. So how do I account for that? And I was getting confused, and I couldn't understand it all together. And then I thought, but wait a minute. And I thought, if the rock is sinking and the wave is being produced, then it's like more like a vortex. And when I thought of that, it hit me. Oh, wait a minute. I'm thinking in 2 dimensions. You see how that flat two-dimensional planes get you? You know, that Euclidean flat space? Well, in this way, you know, we think of waves as like, you know, traces on an oscilloscope or something like that. But actually, a wave is a three-dimensional vortex. I realized, oh my God, if this was in 3D, this would be a vortex along an axis of rotation. And it hit me, oh my God, waves are 3D things. We live in a 3D world. It's not a flat thing. Flatness does not exist. There's no such thing. That's a concept of man, not a fundamental structure of nature. Euclidean flat space are irrelevant to nature. And so I totally got it, and I thought, oh yeah. So, you know, when you think of I looked at the sun and I thought, oh my God, I don't know how many times I thought of a waveform leaving the sun and coming towards me doing this up and down thing. And it's like, you know, not anything in the universe does up and down. You know, it rotates, it spins. And so a waveform coming off the sun is a vortex that's touching me, that's hitting my eyes, that so on. And I realized that this was fundamental. That we commonly, because, and you know, if you ask a physicist, he'll tell you, oh yeah, it's a 3D vortex, but we don't think of it that way. I mean, if he's well educated, he'll know that. No. And we don't think of it this way because it's too complex. We flatten it up so that well, okay, but if you flatten it up, now you don't have angular momentum. You don't have the spin dynamics of the geometry of space, you know, that generate the vortex in the first place. So I was like, oh, okay. So I'm thinking about all this, and I'm getting excited about it. And I laid back on the, I get excited, you know, you might have noticed. And so I laid back on the side of the lake and I was looking at the sun setting behind the mountaintops. Which happens quite early in Canada. And then I noticed that, well, actually late in the summer, but I noticed that the sun was going behind the mountains, and the thought came to my head, isn't it cool how we always think the sun is going behind, but actually it's the earth that's rotating? And when I thought that, something hit me. Another thing hit me. I realized, well, these waveforms, dynamics, have to do as well with motion in space. Things move not in this up and down motion. And then I thought, wait a minute. And I thought of the solar system, and it hit me. Typically, and if you have children, please, if they go to school, they're all going to get told that the solar system looks something like this. Let me try to erase this. Okay, that the solar system looks something like this. That the sun is in the middle, and the solar system, and in my school, we even had a little machine with a little thing, a little crank you spun, and the earth went around the sun with the moon and everything. And so they tell you, oh yeah, that's the sun, and then the planets go around like this in an elliptical course, and depending on the interaction of all the planets, it's either elongated or more round. Or you got all the planets like this in the solar system. Well, actually, that is absolutely incorrect. Okay? The thinking of the solar system in this matter is equivalent to thinking that the Earth is flat. The solar system does not behave that way at all. In fact, the solar system it behaves in a completely different way, since the sun is moving through space and the planets are flying around the sun, generating these huge vortices as it follows the equator of the sun. That is a completely different picture. All right? It goes from flat to spacious, to movement through space. And that makes a big difference. All of a sudden, you start to see that even planetary motions, solar motions around the galaxy, galactic motion, supercluster motion, and so on, all have this elliptical, vorticular dynamics of space. They all have this torque dynamic through space. And if you look at the Earth on this vortex, you could say that this is 2000, 2000 for instance, and this would be then 2001, and then this would be 2002, and this would be, this is extremely long distance apart. Millions and millions and millions and millions of miles apart. There's nothing in there, the planets do not come back onto their path. They don't. If they did, we most likely would have the same set of information over and over and over, like a broken record. Okay? And we'd probably get real bored. It would be like Groundhog Year, And so, what makes, and so it hit me in my head, oh my God, what makes every second, every billionth of a second different from the other, every part of the division of space-time different from the other, and why is information changing? Is because we are never moving back onto the same coordinates of space-time. We're moving through space-time, gathering information through the system and feeding it back and modifying the structure of space as we move through it. So it was really an important realization. It had implication in the physics I was writing, but as well it had implications in psychology theories and stuff that I was interested in, because you could, and I've experienced and experimented on this since then, where if I give this visualization to somebody and I ask them in their mind's eye to move the Earth back along that vortex to an instance, to something that happened in their life that was traumatic, I'm able to get these people to go back to that moment in much more vivid and much more powerful way. And then what I ask them to do is to change their visualization of that experience from their perspective to the 180-degree perspective, like to the perspective of the person that assaulted them or whatever. And then they get a new set of information. And what I believe happens is that new set of information is encoded in that place in space-time. And so all of the rest of the information is changed from there on. And that is actually the effect of psychology, asking you to go back to an instance. But if you don't know, and I think that's where psychology could get some help from this theory, is that if you don't know the true dynamics, the fundamental mechanics of that motion through space, you're going to try to visualize it in something that's going back in time on the same record, broken record, so you can't get there, right? But here, I've had instances where people were able to do that and solve some very, very important issues immediately. And what happens is that if they're there in present time, then all the geometry that catch up with them now opens a whole new sets of geometry for them in the future. So that was really exciting. So I was on this bank of the lake, and I'm thinking, wow, I've got something here. I gotta think about. I want to do an experiment, to do something to be able to, show this. Am I correct? And I thought, how could I experiment to show a 3D wave instead of a flat wave? And I thought, okay, well, if I have a spinning motor that would give me the torque of space-time, and I attached a string to it, maybe I could, let's see what it does, you know. So I went back to my van, and I'm looking for an electrical motor. I couldn't use the V8 engine of my car. I was looking around, so I finally found one in the razor that I was using. It was an electrical razor, so I took the head out of the razor and I dislodged the motor, and then my razor was stuck in my experiment for a long time, so I grew a beard. I did. Here's me with the beard. And so, because I had no razor, and so my rope, I took a little fishing rope, and I took a little bit of a weight, you know, fishing weight that had a swivel on it, and I attached it to it, and I turned the razor on. And the result was so exciting. I was amazed at the result, because as soon as I turned it on, it went into coherent waveforms. And I used to go around physics talks with my little razor and my little string, going around showing people about a 3D waveform, and it was kind of funny. I'm going to demonstrate to you what happens when you spin and when angular momentum is applied to a string. And this is what happened here. So if I can have lights down, let me try to get this going. Okay. So here we are. And so we've got little motors that are going to spin this. And here's the coherent waveform. And here, with the strobe, I can stop the waveform that's actually a 3D wave. And can you, everybody see that this becomes a 2D sine waves? And that's how we visualize it. But actually, if I show you the whole thing, then you see that it's actually a 3D vortex, right? Spinning in space. So let me show you again. I gotta change the strobe frequency. There we go. And can you see how it becomes? It seems to be a sine wave, but actually is a result of a vorticular action of a rotating system. Here's a nice stable interference waveform. And interestingly, when you look at the central part of these waveforms, you can see structures that look like Mandelbrot fractal structures. And you can get much more complex one. Oh, this is a simpler one. This is a 2-wave. There's a 3-wave. I like that one particularly. There we go. Here's the sine wave in strobe stop. Can everybody see that? And then you can get, like I said, very complex interference pattern that you would expect from wave dynamics. This is a stable one. There we go. Here's a pulse. Here's highly complex waveform. So, lights up. This is my string theory. And it's a toy, but I think that it's a toy that actually has a lot of significance in the way things work and how physics function. You know, just like a string from string theory, implies a lot of complexity in string theory, but it's only a string. Well, in here, you can start to see how the string, but I want to make clear here that I'm describing the string not in terms of some, esoteric 26-dimension theory, but actually as a structure of space-time torque itself, so that what we see is the electromagnetic field coming out as space-time torque radiating after it has been contracted into the system and forced angular momentum. And so that the feedback is continuous. And those lobe structures that are generated when the string goes into stable harmonics resemble very much the lobe structures that I was getting when the spheres are intersecting in this geometry. So I continued to explore these dynamics, and then I realized, well, sure, there was crop circles that looked that way, but one of the first supernova, I think it was the first supernova ever to be photographed, is supernova 1987A, and this picture was taken just as the action occurred, and it stunned astrophysicists all around the world that, when you expect an explosion of a star, you don't expect highly structured field to be generated like that. So it created a lot of stir in the physics community. And I got really excited because I'm like, wow, they took a picture of the geometry of space, my God. And I thought there was enough energy there that the plasma dynamics actually illuminated the dynamics of space that were going on. And I called my local astronomer, and he just told me I was nuts. And basically, he told me, oh, well, it was just a fluke. It's not going to happen again. Then a few years later, this one was taken. It's called the Hourglass Nebula, and sure enough, it did happen again. And now they've made recently they've made new models of how this could happen. Why is this happening? And they found out that it actually in 3D, this is actually a double torus. It's like two toruses, and the reason is that the star blows off the top and the bottom. It follows the vortices. It's the easiest point of exit, and all the matter goes out and then goes out this way, and it expands a double torus, but viewed from various angles, it looks like so. And so that's very confirming. And I was really excited about it. And those supernovae dynamics, when you look carefully, are very interesting because you got this eye in the middle, and it's looking straight at you. And when you look closely, it even has a little twinkle in the eye. And the twinkle might be because there's other gases of different densities that organizes in the middle, and here you can see actually a fractal structure. You see the orange first hula hoop are reproduced in a smaller fractal version in the middle of the system, and so on. So you're starting to actually see the fractal nature of the field there in different gas densities. And really, when you solve Einstein field equations with the torque, people could say, well, okay, but you're adding torque, but what's creating the torque? And the answer for that is that those equations are based on Laplace-Poisson earlier equation, which are equations of density. And what that means is that the density of the field is what drives the space-time torque. That is, because there's different vacuum density from infinitely dense to infinitely undense, but never absolute vacuum, then just like high pressure, low pressures of gases in our atmosphere generates a hurricane, then you get a galaxy, or you get a star, or you get a planet, or so on, because there's density change that drives the whole system. From infinitely dense to vacuum state, you know, in the extremely large. So you can see that these change that occurs in supernovae dynamics, they resemble very much what we just visualized with the little string ray machine. Here you get the same kind of dynamics. So here you get a hurricane, right? This is off the coast of Florida, and here you get a galaxy. Completely different scales, same dynamics. What do you find in the center of a hurricane? The eye of the hurricane, which is stillness, which is the vacuum state geometry, which is the place where it gets the coldest. And then at the center of the galaxy, you find the black hole, where past the event horizon, all thermodynamics are absorbed and so on, and you leave behind vacuum state geometry. So same dynamics at completely different scale should tell you something about that force and about these change of density. Imagine the change of density between galaxies, which in fact only brings molecules centimeters apart. And then the density inside a galaxy, which is much higher. And then the density inside the solar system, which is much higher. And then the density on the surface of the sun, which is much higher. And then again and again and again, because things are not homogeneous. They have different viscosities and different densities, which drives the space-time torque. This is a picture that was taken at the Sydney University of the energy levels, the energy dynamics around carbon atoms, molecules. And so here we see the same vorticular, you know, dynamics of the space-time torque, according to my views. And we'll get into very high scales level. This is surveys that were done of superclusters of galaxies that's extremely large. And when they looked that far, they expected that things would be quite chaotic and not organized and so on. And instead, they found the exact contrary. These very large scale structure organizes in octahedrons and tetrahedrons array way out there. And these papers are actually published in literature and called a fractal or egg carton universe and stuff like that. That's what they're seeing out there. And basically, it's just like this. If you got your nose in the rug, if you got your nose in a Persian rug, there's no way you're going to think that there's a pattern to it. You're just going to think it's all chaotic. But if you get far enough from it, if you change your scale relationship, all of a sudden you start to see the pattern appear. And that is what I believe we're starting to see is the actual structure of space-time and how it organized matter. Even the table of elements. That was extremely large. Now we're going to much smaller atomic structures. Even the table of elements has been solved by Dr. Moon at the Chicago University to be able to solve for all the protons, neutrons interaction using the 5 Platonic solids, very specific geometry, and then even all of the electron interactions using the Academian solids and the vector equilibrium and so on. This is Dr. Moon, the late Dr. Moon. Oh, well, that's one of the statements he did at the end of his life. We are entitled to seek geometry, to seek a geometry of space, or in other words, we are no longer able to talk about empty space. That is, from his findings, he figured that there's got to be some geometry in space that's dictating those particle interactions. If you go even smaller, now you're getting to the electron clouds and the orbitals, you find that these probability orbitals match very specific geometries that have to do with tetrahedron and octahedrons. The group theoretical models that predict subatomic particles are based on geometry. I mean, they emerged from crystallography. That's where these models came from, except that typically physicists ignore the geometry. They say, no, that's just a way to solve the equation. I believe that the equation is solvable in geometry because the geometry is fundamental to these particles' interaction. You have to have that geometry to be able to solve it. And, you know, we find that these interacting, these group theoretical models match the isotropic vector metric, the vector equilibrium, and so on. So now we're at the extremely, extremely small. Well, how does this